Um, let's get to it. And we've got Mr. Trapp online. Hello, Mr. Trapp. Uh, he was not coronavirus. Yeah. So looks like we're missing Mr. Lee also. This is a sad morning. Okay. Well, looks like Trapp's online, so that's good, right? Um, and okay, so let's get to it then. Um, so the first thing we want to start talking about, basically for the rest of the semester, what we're going to do is talk about multivariable functions. So these can be simple, or they can be, grandiose. So for example, we could have something like something as simple as that: f of xy equals x squared plus y squared. So it's a function of two variables. And what does that mean to do? Well, you just plug in numbers like you would, but this time, who goes in for x, whatever the first coordinate is, and who goes in for y, whatever the second coordinate is. Okay, so for example, what would, let me pull this up here. What would f of 2, 3 be? Right, okay. What is 2 squared plus 3 squared? 13. Okay, great. Okay, so, great, right? So that works just like functions of a single variable, except there's more letters, and you plug things in the proper order. And the order in this case is defined because I said f of x comma y, but like in the next example, I had t of x comma y comma t, and I just made something up, something like that, okay? So it's important to know what the order of the variables is, because on that one I said f of x, y, t. Could I have said f of t, x, y? Sure, right? I could have put them in whatever order I wanted. There he is. But I need to specify that order so that you know where to plug in what, right? Because otherwise this isn't going to work. And we can have, more complicated things. So what's your favorite chemistry equation, right? Which I could solve for any of the variables, of course. And so, for example, if I solve for pressure in terms of the other guys, then pressure is nRT over V. And how many variables are there, by the way?
Well, 5 if you count like both sides.
Okay, so 5 if you count both sides, but really, how many are there? It's really only 4, because what's true about R? Yeah, R is a constant. That's the universal gas constant, whatever the heck it is, right? So the variables here are P, pressure, N, the number of moles, T, the temperature in Kelvin, and V, the volume, right? Oh, me saying temperature reminds me, guess what I forgot to do this morning?
Change the temperature?
No, my COVID thing.
You want us to show you ours?
No, but I just totally spaced on doing it before I came to work this morning. Yeah, so I guess I'm breaking the law. Um, yeah, breaking the law. Okay, so anyway, you know the Judas Priest song? Yeah? No? Okay, whatever. All right, so anyway, in this particular example, right, R is a constant, but whatever, right? I just wanted to show you that, multivariable functions are things that you've actually already been dealing with, right? Because you all took chemistry in high school, yes, of some sort, unfortunately. But you've all seen PV equals nRT before, right? And if you haven't, then how you managed to get admitted to college is beyond me, but whatever. Um, okay, so great. Right, now then, um, if I want to, so let's take this first example and let's interpret that geometrically, okay? So if I had a function that was like y equals f of x, well, let me not use f, let me use g. And let me just say pick x squared, right? How do I graph that? Yeah, you do the t-chart business and you end up with something that looks like that, right? A parabola. Okay, so what's my coordinate system? Well, I have a grid. It has x coordinates, it has y coordinates, and that's how I plot things. You guys have been doing that for years, right? Okay, so the question is, how do we do this for 3 coordinates? Right, so how do I do this sort of graphical business with my first example, which was f of x, y? I'm going to call that z. And so now, what kind of things, what kind of points am I going to be drawing? They're going to be points in how many dimensions? 3 this time, right? X and a y, and then a z. So how do we orient our coordinate system to draw this? And this is a pain in the butt to draw, but you guys will have to bear with me. Okay, so what you're looking at is x and y are along a plane that's parallel, say, to the floor of the room, and z is sticking up perpendicularly out of the floor. Okay, and I've tried to draw this with a bit of a perspective. Okay, now it may surprise you that x comes out towards you and y goes to the right. Okay, but think about it this way. If you were sitting on top of the letter Z and you looked down, you would want to see X to your right and Y in front of you. Okay, which is the exact same orientation that things were in 2 dimensions. X to the right of you, Y in front of you. Okay, so that's why we draw it that way, so that we preserve this being what we call a right-handed coordinate system. Okay, meaning that, for example, if and I can't bend this way, but if I take my hand and I put it so that the fingers are pointing towards the positive x-axis, and I curl my fingers, which way do they curl? They curl towards the positive y-axis, and which way is my thumb pointing? In the positive z-axis. Okay, so that's what I mean when I say it's a right-handed coordinate system. Okay, now, if any of you are left-handed, are you left-handed? You can use both. Wow, that's impressive. Yes. Uh, yeah, if you look down, well, no, you would see all 4 quadrants in the plane, but 1 and 4 would be to your right. Yeah. Yes. Okay. But the reason we say it's right-handed is because of that finger curling kind of thing. And those of you who have, how many of you guys have seen the cross product of vectors in physics? So like torque, for example, right, is force cross radius vector, or the force of a magnetic field on a charged particle is, or an electromagnetic field is QV cross B plus E. No? Okay. So anyway, the cross product, you use this right-hand rule where you curl your fingers and you use your thumb, and in physics quite a bit, okay? And if those of you who go on to take linear algebra next semester, which, how many of you guys signed up for linear next semester? 1, 2, no? No? Donovan? Cole? Public shaming time. Okay, that's fine. Um, yeah, you guys will talk about the cross product and stuff more in that class and the vectory kind of stuff. Okay, but that's the orientation here. So if I take, what did I plug in, 2 comma 3 as my example, right? So we said that f of 2 comma 3 was, excuse me, 13. Okay, so how do I graph that? Well, I go 2 units in the x direction, 3 units in the y direction, and that defines this little red point here. Okay, and this red point is at 2 comma 3 comma 0. And then what does the 13 tell me to do? Go up 13 units, okay, which is outside of my picture because that's a big number. But so that point, the red dot that I've drawn, 230, is in the xy plane, and 23 comma 13 is just 13 units straight up from it vertically. Okay, does that kind of make sense? Yeah, and it's really hard to draw these. Now, one thing that I really like about the book, okay, is so first off, as with the stuff on polar coordinates, this is in volume 3 of the book, not volume 2. But if you download volume 3 of the book, the color version with interactive diagrams, and you open it in a PDF viewer, the diagrams, you can actually rotate them, right? They're three-dimensional, so they're all fully interactive. So you can kind of look at the different graphs from different angles and get a much better sense of how this stuff looks. No, it can. Mathematica can do everything and make you a sandwich. Okay. Well, not quite, but yeah. In fact, maybe I should suggest that as a feature is that it needs to like Mathematica needs to have an interface to like a panini press machine or something, so that you could have like make sandwich, and it would, yeah, it can do everything and make you a sandwich. Yeah, yeah, we'll make millions, right? Okay, so that's the idea here with the functions. Okay, all right. So let me take another function that's not quite so simplistic. Or let's see, Dr. Insaldi called this one G, so let me just stick with it. Okay, so like with single variable functions, we have to worry about things like the domain, the range, all the stuff that's sort of calculus involving. Okay, so what does the domain mean generally? The domain is the set of numbers or points that you are allowed to plug in, right? Okay, now in single variable calculus, it was a set of x values. Okay, but in a multivariable context, what will this be? It'll be a set of points, right? X comma Y. Okay, so what values of X and Y are we allowed to plug into this square root function? And I realize my handwriting is terrible. It's supposed to be a 2. Okay. Well, what are we allowed to plug in and what are we not allowed to plug in? What's required, Jack? Or equal to. But yeah, okay. So we've got a square root, right? So whatever's underneath that square root symbol cannot be a negative number. Okay, so the domain is all x and y that satisfy that inequality. Yes, Kim. Yes, we do not consider imaginaries for this. Uh, in complex variables, which is like a 300 level class. Okay, so it may seem surprising, but imaginaries really complicate things in both beautiful and irritating ways. So, anyway. Okay, so our domain is the set of all x and y that make that true. Now, if I move the x squared and the y squared to the other side, then I actually have this inequality, right? Because, of course, x squared plus y squared is always a positive quantity anyway. Well, what does x squared plus y squared less than or equal to 9 describe? It's a circle with everything on the inside too. Yes? And the radius of the circle is less than or equal to 3. Okay? So this describes all points that are no more than 3 units away from the origin. Okay, why 3? Because that's the square root of 9, right? So x squared plus y squared equals 9. Do we all agree that that's a circle of radius 3 from high school? Yeah. And then the less than or equal means it's everybody on the inside too. So it's not just the circle at the boundary, but all the inner stuff too. Okay? All right, so let's plot this thing with all Mathematica and switch the stream over to old Mathematica, maybe. All right, so what I'm going to do is I'm going to define a function, g of xy equals square root of 9 minus x squared minus y squared. That's the example Dr. Insaldi picked. And then what I'm going to do is I'm going to do a, well, let me just start this way. Okay, so with a regular plot, I need to specify what function am I plotting and what range of values of x do I plot. Well, if it's a multivariable function, then I need to specify what's the function and what's the range of x and y. Okay, and in this case, I picked -4 to 4 because I knew that that would capture all of this circle that we've been talking about. Okay, and if I run this, then why did that not plot? Oh, Mathematica wants to be annoying. There we go. Be annoying this morning. Okay, so what do we get? It's the top half of a sphere. That's cool, right? Okay, and can we see why the domain is therefore everything x squared plus y squared less than or equal to 3? It's that circle that's along the base there. Okay, so this is kind of like one dimension up from a circle, right? If I did f of x is 9 minus x squared, we would be graphing the top half of a circle. If I kick this up in one dimension, what am I graphing? The top half of a sphere. Well, that's cool.
So, if it's a circle, why doesn't it turn into a cylinder?
The domain is a circle, okay? But the range is what happens when you plug it into that function, right? And so, yeah, if we were just talking about the domain only, then yeah, you would be thinking of a cylinder. But the plot, of course, is the x comma y comma whatever the square root of 9 minus x squared minus y squared is. Okay. Okay, so does that make sense? Yeah. Yeah, exactly. Well, square root of sum of squares type thing, but yeah. Okay, so we get a sphere. Great. Now, if you notice on the plot there, you see how it's Mathematica has drawn some thin lines in black. Okay, these are called contour lines. Okay, so if I kind of rotate here, you see that it's diced up. I mean, almost imagine like this is an onion, right? And if you were to dice an onion, how would you do so? You would do a bunch of cuts one way, you would do a bunch of cuts parallel or perpendicular the other way, and then you would do a third set of cuts this way to get diced onion, right? And depending on how skilled you are in the kitchen, you might do those cuts in different orders, but that's basically it, right? So it's drawn the cuts that are perpendicular to the XY plane, right? Cuts one way and cuts another way. It has not drawn the cuts that are parallel to the XY plane, which would be the hard ones to do with a knife. Um, I don't know. How many of you guys have ever diced onions? You've watched people dice onions. You know, my favorite way to buy dice onions? You go to Walmart and you go to the produce section and you buy the 8-ounce container of pre-diced onions. And then well, there's that, but I mean, you're going to cry when you start cooking them, but yeah. Okay. So I could slice this thing up in three different directions, and doing so is called a contour plot. Okay. So let me take the exact same code here, except what I'm going to do is change this to contour plot. Okay. And if I do so, this is what I get. All right. So let's interpret what the heck are we looking at?
Well, it looks like the slices, but they're increasing by smaller amounts from the inside.
Yeah, okay. So which way are we looking at the sphere here, or the top, the hemisphere? We're looking at it from what point of view? Huh? The top of it. Yeah, it's like we're looking down from the North Pole onto the Earth. And what we would see is a circle. Okay? Now, on this picture, why do we have concentric circles here, and what's with the color scheme? Okay, well, what would be true about the points that are closest to the center of our point of view? They're the ones that are physically closest to us, right? And the ones that are down around the base of the sphere are the ones that are physically furthest away from us. Does that make sense? Yeah? Okay. So what we're looking at here is actually a topographical map of the sphere. Okay, so let me put that and that. No, it's more like imagine that the sun is directly above the North Pole, like we've got a big flashlight, right? Yeah, the colors are kind of representing how far up or down this thing is, okay? So here, the dark bluish color around the perimeter is like the equator of our hemisphere, and that's the furthest away from us and also lowest in the figure. Okay, and then as we go through this orange to the sort of brighter yellow color, we're coming higher and higher in Z. Okay, so each of those circles that are drawn are a constant value of Z, um, and a constant value of Z would be a circle because it'd be a number equals square root of 9 minus x squared minus y squared. That's a circle, right? And as Z gets bigger, the circle is higher up but smaller. Okay, does that kind of make sense? Yeah? Now, you guys have all looked at topographical maps before. Okay, so let me flop over for just a second to a real topographical map to kind of illustrate what I mean here. All right, so let me switch the input on Elgato to preview. Okay, so let's look at something like this. Okay, so you guys have all seen maps like this in your life, hopefully. Well, okay, let me rephrase. How many of you guys have played Zelda Breath of the Wild on the Switch? Oh, well, that was a big old womp womp. Yeah, okay. Well, anyway, the map mode is very topographical and it's super useful in that game. But anyway, so we've got this map here. I have no idea where this is, but I stole this picture from Wikipedia. So we have this place called Stowe, and there's this other place called the Lower Village. This is probably in Colorado or something. Okay, and what do all of these contour lines mean? Yeah, they're all lines of constant elevation. Okay, and you also see some numbers. So, for example, over there toward the left at Katy Hill, how tall is Katy Hill? Well, 1122. Yeah. So it's 1122 feet, presumably, above sea level, presumably. Okay, but then if you go a little bit down from the top of the hill, you see there's this line here that has 1,000 on it. So that means that if you were to follow this line, you would stay at a constant 1,000 foot elevation, right? So what you would be doing is kind of walking around the peak. Okay, does that kind of make sense? Okay, yeah, it would be kind of rough hiking, but you guys like can see, if you see this map, can you imagine what this place actually looks like in terms of, like, I've given you a two-dimensional piece of information, but you can sort of imagine a three-dimensional world based on that, right? That's exactly what I just did with the sphere, only it wasn't quite as gloriously exciting. What little circle? Yeah. Oh, yeah. So that would mean that, like, there's probably a little dip and then it comes back up to a little hilltop. Yeah. Um, yeah, but the lines that are drawn are lines of constant elevation. And then the idea is that, like, let's say between the one that says 1,000 and the one that says 900, there's a bunch of lines. So that's probably every, 20 feet or something, right? And so you could look at this and you could say, okay, like, if I want to get from Katy Hill to the lower village, what's the fastest way to do that? Right? If I were here and I wanted to get here, I'd probably want to walk like this, right? But if I did so, that's going to be pretty tough hiking because I'm going to be going down very steeply. Okay. How would I probably do it if I were really hiking this? Yeah, if I do kind of like switchback wiggles. Okay. But you guys, like, how many of you have actually gone hiking with a map like this? Like, none of you were Boy Scouts? Really? You're going to learn this in your military service, Kim. I can guarantee you that. So you might as well learn it now. Um, okay, but anyway, the contour plot that I made is basically like a mathematical version of this topographical map. Okay, and so what we want to do is we want to understand, like, what can we learn from this topographical map, and then how can we start to translate that into the language of calculus? Okay, so for example, let's take what we just said. If I walk from Katy Hill to the lower village directly, what could you say about my elevation as I'm making that journey? Definitely not constant. Okay, that makes sense. But I'm going down. At what rate am I going down? No, not some freaking integral. It's a derivative, right? Okay, but I would be well. Okay, let's put it this way. If I went, so let's take imagine a line that goes from Katy Hill to this river, okay, perpendicular, right? If I follow that line, I'm going down as steeply as possible. That's like the most difficult downward hike I could make, right? So what we would say then is that the derivative, quote unquote, and we'll specify what we mean there, is most negative along that particular path, okay? Now, what about if I'm at Katy Hill and I walk, well, let's see. Uh, Actually, let's say I'm along this 1,000 foot contour that's sort of around Katy Hill, and I walk along that contour. What is the rate at which my elevation is changing? Zero. I'm not going up and I'm not going down either. Okay. And could you guys imagine that if I walk just ever so slightly off of that 1,000 foot line, I would be going down, but it would be a pretty gentle slope going down. Okay. Whereas if I were on that 1,000 foot and I put it so that the 1,000 foot contour was directly behind me and I walked forward, I would be going down, but at a faster rate. Yeah. Well, words like rate, faster, direction, this all means derivatives, right? Oh, so we have to start talking about calculus to really answer these questions. Okay. Now, what would you say about my elevation if I walked along the riverbank? What do you think would be happening? Well, okay, it would be probably very, very slightly decreasing or increasing, depending on which way I'm. Yeah, exactly. So if I walk along the river from the southwest to the northeast, okay, we'll assume that north is straight up on this map. It doesn't say. Yeah, well, there's those little dots, right? So 657, and it's if we follow the river, it looks like if we would be walking from southwest to northeast, we would be going upriver. Okay. And that kind of makes sense because look at the size of the river towards the top of the map. It's smaller, right? So it's probably a couple streams are coming together, and the water would be flowing from the northeast to the southwest in this map, right? So if we walk along the river, our elevation would be changing very, very gently as we walk upriver. Okay, and if we walked the other direction, our elevation would be changing very, very gently but negative, right? Because we're walking downriver. Okay, and if there were, like, let's say there's a lake, right? So see, just south of the lower village, there's this little pond or lake, right? This guy. What's the elevation along that lake? Some constant, right? And that makes sense because lakes are kind of pooled bodies of water, and the last time I checked, they're not lopsided, right? Because gravity, yo. Um, yeah, okay. Not just a good idea, it's the law. Yeah. Okay. So does that kind of make sense, though? The kinds of questions that we would want to ask that are sort of calculus in nature based on a picture like this? Yeah. Okay. So let's take the same thing and let's go back to Mathematica and kind of ask those exact same questions. Right. So let me. Um, oops. Okay. So if we go back to Mathematica, right? If I'm looking at this sort of topographical map of the sphere, well, where's the peak of the sphere on my map? It's in the middle, right? That makes sense. I'm at the top of the sphere. Okay. Which direction would I need to move to go down? Any direction once you're at the top. Okay. So let's say I move straight upwards. Okay. So north. So I start here and I start walking there. What's true about the rate at which my descent changes? Yeah. Steeper the further I get towards the north, right? And that makes sense. If you're on the top of a sphere and you, right, and then it gets steeper and steeper and eventually you fall over. Okay, so we want to understand, therefore, the calculus of how we can explain that. Okay, so does that kind of make sense? The where we're going with this? Okay, so let me switch back over to where did I put it? I don't. Oh no, here it is. Let's switch back to that, and then I need to switch the preview. Okay, so back to the preview. Okay, so all right, so what we've basically done here is we've talked about level curves. So if I take a multivariable equation, so z equals f of xy, okay, let's take as our example x squared plus y squared. Okay, so new example. If I hold z constant, then at the value z naught, then z naught equals x squared plus y squared describes circles. Yes? And their radius is bigger depending on how big z naught is. Okay, does that make sense? All right, so let me draw one of these in Mathematica, um, just for sake of time. All right, so let me go back to Mathematica and switch the inputs. Okay, so let's do, I've already used G, so let me use F. Okay, so this time, this is what it looks like. All right, now what does that remind you guys of? I was going to go with the thing at the end of a Looney Tunes cartoon, right? That's all, folks, right? Yeah, okay. But how should we read this? Well, what's true about the stuff, the dark blue region? How should we interpret dark blue going through the oranges into the yellow at the edges?
Well, I think that would be farther down.
Right, the dark blue is further down. Yeah, so it's like an inverted cone or something like that. So this would be kind of like what we would see if we were looking at a lake, right? Let's say that the blue is the water level, and then so it'd be like oh, I don't like Crater Lake, right? So let's say that a meteor hit the Earth, made a perfectly circular crater for us. It's great, and then then it rained. Yeah.
Wait, how did this? I'm confused on how this would look like the lake.
Well, okay, it'd be like a lake that's surrounded by right a hill.
Oh,
Yeah.
yeah.
Okay. So that's the contour if we hold a z constant. If I hold x or y constant, okay, so what I'm going to have to do here is a little bit funky. Let's see, I want to do, um, let me hold x constant at 0. Okay, what do I get that direction? What are these shapes?
All right. So when you change the
So I made x a constant, and I just picked 0. And I did z minus f of xy so that I have this thing as a function rather than an equation. All right, now z equals f of 0 comma y would be z equals y squared, right? What kind of curves are z equals y squared? Those are parabolas, yes? Big shock, look at what we have, okay? So if I have a surface, and imagine a surface in 3 dimensions, and if I slice it horizontal to the ground, I got circles. If I slice it perpendicular to the ground, I get parabolas. Okay, so what do you think this whole thing looks like if I were to actually do a 3D plot? Kind of, except upside down. Okay, and it's slightly different because there's no square root here. Okay, so it basically looks like a parabola that has been revolved around the z-axis. Okay, now here, let me change the plot range here because to make it right, so it's kind of like this, but it keeps going up, right? So it's like the bottom half of an egg or top half, depending on your point of view, right? Are you a big Indian or a little Indian? ENDIA. It's a computer science joke. So, okay, does that kind of make sense though? Yeah. So you see those black lines that are on the sort of orange surface? Those black lines are the parabolas that we saw a minute ago, right? So that was us slicing our very weirdly shaped onion. Um, huh?
it's like weird process how these all like put together.
Yeah. So I don't know. I mean, this might look like an egg carton, right? Because that'd be a perfect little place to put an egg inside that little bowl, right? Okay. So does this kind of make sense? And I know this is hard to visualize, but the fact that you guys have a textbook with interactive 3D diagrams and Mathematica, believe me, is going to be is a godsend for you guys because back in my day, When I was learning this stuff, you know what I did not have? Any of that. And so how did I learn all this stuff? I had to imagine all of it and draw pictures. Well, I didn't know Greek yet. Okay. But yeah, I had to learn how to imagine all of this stuff. And for once, my video game hobby paid off because think about what you do when you play a video game. You're looking at a 2D screen, but yet you see a 3D world, right? It trains your brain to think in a particular way and to interpret 2D information in a 3D way. Well, this is similar, it just requires a different training. Yeah? Yeah. Well, that's cool. Yeah. Okay. So let's continue with our discussion. So let's go back to now let me make sure. Let's see. Let's go back to preview and all right. So we talked about the level curves. Okay. And then the topographical maps. Okay. So let's talk about this a little bit more um, in terms of where we're going to go with this in calculus. Now, if I walk due east, what is true about my x and my y coordinates if I walk east? Yeah, x is changing and it's increasing, and y is staying constant, right? If I walk horizontally on my map. Okay, what about if I walk north? Y changes, but x stays constant. Okay, so walking north increases your y, walking south decreases it, walking east increases your x, and walking west decreases it. Okay, that's our usual coordinate system. Okay, does that make sense? Okay, so what we want to understand then, so let's take, for example, that we are at, well, let's pick a point here. Let's pick, um, well, let's see, where would be a good point to pick? All right, how about where the town is? The town of Stowe. There's the capital S, okay, and there's three dots immediately below the capital S. So let's say we're at one of those dots, okay? If I walk east, what would be true about my elevation? Would I be going up or going down? From the little dots just underneath the Stowe on the map. Yeah, I'd be going up, okay? So what I would say is that my derivative in that particular direction was positive, okay? And how positive it is depends on how steep that slope is, right? So if it's like a really, really steep rock face, that would be like a slope of like 1,000 or something. And if it were like a really, really, really gentle hill, it might be a really small slope, okay? And if it's somewhere in between, then numerically it's somewhere in between, okay? All right, what about if I walk west from that point? What does it look like? Is my derivative would be? Yeah, we could argue about that based on the detail on the map, but it's either going to be very gently negative or maybe zero. Okay. All right. Now, what about if I walk north from one of those points? Would I be going up or down? Maybe very, very slightly down or staying at level, right? Depending on exactly how this town looks. Okay. But what about if I walked south from there? Would I be going up or down? I think I'd be going up, but somewhat gently. Yeah? Okay. So what we're talking about here is called partial derivatives, meaning what is the slope if I hold one variable constant and look at the rate at which z changes with respect to the other variable. Okay. So for example, if I go back to Mathematica for a moment, and let me change the plot here. All right, so let me go back to my contour plot. Here, I've held x constant at 0. Okay? Um, and I've said, all right, if I asked you what the slope along one of these parabolas would be, would you be able to answer that question? Okay, if the parabola has equation z equals y squared, well, it's at some points at 0, but what would it be in general? No, not average, but just what's the slope? What? Well, it'd be the derivative, right? You draw a tangent line, you figure out what the slope is, and if the equation for this guy, one of these parabolas, is z equals y squared, well then, what would the derivative of z equals y squared be? Can I get a 2y? Right? Well, that makes sense. All right, what about if I pretend that y is a constant and hold x fixed? Well, then I would have things like z equals x squared. Well, what's the derivative of that? Huh. So it's kind of like if we slice this surface up and we hold one of the variables, either x or y constant, then um, we can talk about the derivative because now we're back to something that only has one variable. Z is a function of y or z is a function of x. Okay, which means in the different coordinate directions, we can do all the same calculus we've done before, right? But we can do so much more. And that is what we'll talk about on Wednesday. Okay. All right. Yeah, I know, right? Like, I really have the theater down here. Okay. So, um, basically, before next time, okay, please do this for me. Go download the 3D color enabled interactive version of volume 3 of the book, right? Just Google Apex Calculus and then find it. Okay. Go into this section. This was 12.1 and read through it, but then play with the diagrams, right? And that will really, I think, help y'all's mental imagery here for how to kind of visualize and imagine this stuff. It is not easy, but it is a skill that you can learn by practicing, and it'll be a lot easier than it was for me because I had to walk uphill both ways in the snow, 10 miles both ways uphill, dodging murder hornets and whatever else, right? That without shoes. And all right. All right. Well, I will see you guys on Wednesday.